This is the story about the era of mistakes, of how the geniuses of Europe tried and failed to discover spin for 5 years, until a bunch of students came along to discover it for them. Part 1. Otto Stern tries to disprove quantization. Okay, so let's recap. It's 1915, and a scoundrel called Niels Bohr has been going around saying that the emission spectrums can be explained by the quantization of the electron orbits. Basically, he's saying that when an atom absorbs heat, this raises the electrons to higher orbits. But this is unstable, and so the electrons fall back to lower orbits and they release the extra energy as light. This would explain why gases only emit a few colors of light when we heat them. Each of these spectral lines corresponds to the energy difference between two orbits. Then Jun Ishiwara learned about this and he was convinced. But he also had a question. How can we predict to which orbit will the electron fall? And nobody knew. So he also found a way to find the answer. And it is this equation. The focus of this video is mostly on the history and not so much on the mathematics, so I won't go over how he deduced this equation, but this is what it means. If the orbit and the momentum of the electrons are quantized, then they must be described by functions whose integral is equal to an integer multiple of Planck's constant. If you're familiar with analytical mechanics, you might recognize this as action. And in fact, you can think of this as the quantum action equation. I should also mention that Ishiwara wasn't the only one to find this equation. Others like Sommerfeld and Planck arrived to it independently, but in this video I'm gonna call it Ishiwara's equation since he was the first to find it. This equation isn't really taught in universities anymore, but it is really important because at the beginning of quantum mechanics was synonymous with finding solutions to Ishiwara's equation. Let me give you an example. Let's say you want to use quantum mechanics to understand the emission spectrums. Well, first you're gonna need a mathematical model, something that approximates the real world even if it is imperfect. For example, the harmonic oscillator. The nucleus attracts the electron. Heat pulls it away, but then it comes back, and in the process it releases light. We are gonna model this interaction as a spring. Heat is gonna be a force that pulls on the string, and then the frequency at which the spring resonates is gonna be the frequency of the light. Using this model, we can get functions that represent the position and the momentum of the electron. But remember that these functions must satisfy Ishiwara's equation, and at the same time, they must result in the frequencies we observe in our experiments. And so we have to tweak these functions until they satisfy both of these conditions. And once we do that, we can assume that these functions are correct, and we can use them to make predictions for situations that we have not been able to measure. As you can imagine, tweak isn't a very precise word. This is basically a series of educated guesses. And the reason for that is that solving an integral equation is really difficult. If only we had a differential equation, this would be so much easier, but alas, at this point in time, they didn't have it. But what matters is that this worked. For example, Heisenberg was able to use a version of this equation, adapted for 2 electrons, to make a mathematical model of the helium atom. And this model correctly predicted many aspects of its emission spectrum. The problem with using Ishiwara's equation is that the solutions are extremely complex. So complex, in fact, that the only way to write them is as infinite series of simpler functions. These are called Fourier series. And of course, 3 Blue 1 Brown already has an excellent video about it. Although I should mention that in practice we only use like the 2 or 3 first terms of each series, and that usually gives you a decent approximation. But at this point you are working with an approximation of how you think things works. It's not really good. But hey, progress is progress! For this reason, more and more scientists were converting to the gospel of quantum mechanics. And in 1919 there was a conference about it. I'm not sure what they said at this conference, but I imagine that most of the people who attended left convinced that quantum mechanics was a good idea. Except for one, Otto Stern. He left the conference with the determination to prove once and for all that quantum mechanics was wrong. But why was Otto such a hater? What was so wrong with quantization? Well, in principle, nothing. Otto had no problem with the quantization of energy nor momentum. But he had a problem with the quantization of the orientation in the Zeeman effect. The Zeeman effect is probably the single most researched experiment in human history. From 1915 to 1925, all of quantum mechanics, an entire branch of science, was just using Ishihara's equation to try to understand the Zeeman effect. And it is extremely simple. You begin with a setup to see spectral lines. Okay, so you have a gas, you heat it, you get light, you split that light with a prism, boom, you get the spectral lines. Now, all the difference is that you're gonna add a magnetic field going through the gas. If you do that, the lines are gonna split. That's it! This simple fact drove scientists insane for a decade. Okay, so this is how Bohr, Sommerfeld, and the rest of the quantization gang explained the Zeeman effect. The spectral lines correspond to changes in energy, right? And these changes in energy are due to changes in the orbit or changes in momentum. Basically, the electron is farther away or is moving faster. However, it seems that electrons at the same distance from the nucleus and with the same speed can also have different orientations. Normally, this wouldn't change the energy, but if we apply a magnetic field, it does. The reason for this is very simple. Objects in a gravitational field have more energy the higher they are. Well, objects in a magnetic field have more energy the more aligned they are. And this applies to electrons because they generate a magnetic field by moving around the nucleus, making them basically like tiny magnets. Now, the energy of the electrons depends on the orbit, the momentum, and the orientation. And the fact that the lines split when we apply a magnetic field must mean that the orientations are quantized too. Only some of them are allowed by the laws of nature! This sounds reasonable given the evidence, but in retrospect, this is like when Orochimaru beat Sasuke during the Chunin exams. This is the moment everything went to shit. Or well, quantum mechanics is pretty cool. So not shit, but it is the moment everything changed. Think about it. Before this, if you asked me for any property of any electron, I could give it to you. I could tell you the charge, the mass, the distance from the nucleus, the speed, and then you could go and measure each property for yourself, and you would find the same answers. Measure the same thing, get the same result, right? But now we found a situation where this isn't true. If I measure the orientation of an electron and I tell you, and then you go and measure the same thing, you could have a different result. There's no guarantee. And you might be thinking that, oh, this is fine. Like in life, there are many cases where identical situations have different results. No, we don't. No, that doesn't happen. When that seems to happen is because those situations weren't identical. There were tiny differences between them that we couldn't measure, and those tiny differences are responsible for the differences. But in this case, that's not possible because we are already working with the tiny differences. It is not possible to have less momentum. It is not possible to have less charge. It is not possible to have less mass. There isn't any difference that can explain why we are getting different results. You see what I mean? So when Otto learned about this, he probably was like, how can that be? Like physically, how can that be? One option is that electrons seem identical when they are not, because that difference is hidden. This is one version of a larger theory known as local hidden variables, and it would be a big plot hole in the history of physics for many decades, until the writers finally decided to address it during the Bell theorem arc, nearly 50 years later. And if you want to know how that happened, PBS Spacetime made a recap of that arc, which I wrote, in case you want to check it out. But for now, what matters is that Otto Stern wanted to disprove quantization, and he thought the key to doing that was not using light. If you go back and watch the first episode, which you should do every day, I really need the money, you'll realize that every piece of evidence in favor of quantization was based on light. And for Otto, this was a potential problem because, okay, sure, light was quantized. This had been proven experimentally. But maybe atoms weren't. Maybe atoms weren't quantized, but they looked quantized because we were studying them using light. It's like looking at someone through one of those windows with a square pattern. The person will look as if they are made of squares, but they rarely are. For this reason, Otto needed a way to observe atoms and not light. Otto couldn't do this right away in 1919. He had other stuff going on, but in 1922 he was finally ready. If he wanted to study the effects of a magnetic field on individual atoms, the first thing he needed was a constant stream of individual atoms. And this might sound really difficult to do, but it's in fact really easy. Look. This is a constant stream of mostly nitrogen atoms. And we can do the same with any gas. And luckily, Otto had been researching the speed of particles in metallic gases. And for this reason, he had invented an oven that could turn silver into a gas. Then all he had to do was to just make a small opening on one side of the oven, and that would create a constant stream of individual silver atoms. Today, we know that silver has a special electron configuration, and this lets us measure the spin of an individual electron in the silver atom. But keep in mind that Otto didn't know this at the time. Now that Otto had a constant stream of atoms, he had to send them through a magnetic field. And he chose to use these strangely shaped magnets because the magnetic field in between them is constant and straight. As the atoms pass through, the magnetic field would apply a force to them depending on the orientations of their electrons. If these orientations were really quantized, then there would be only a few possible results. But if not, there would be a continuous range of results. Finally, the atoms would reach a piece of glass where they would cool down and solidify. At this point, Otto had the design of the experiment, but now he needed someone to actually make all the devices. And for this, he commissioned a man named Adolf Schmidt, who was, well, a smith. He made the oven and the magnet. And then he recruited Walter Gerlach to actually perform the experiment. And you might be wondering, why didn't Otto perform the experiment himself? And the answer seems to be because he was very, very clumsy. Think of him as a nerdier Grant O'Brien. Okay, so Otto had assembled his team. They had the brains, the talent, and the muscle. All they needed now was the money. As I mentioned in the previous video, Albert Einstein gave them 10,000 Reichsmarks, which are equivalent to $2,000 in today's money. But even this wasn't enough, because remember that they were going through hyperinflation. Luckily, Otto was friends with Max Born, the same guy who pointed out to Heisenberg that linear algebra already existed. And as a Hail Mary, Max wrote a letter to Henry Goldman, the CEO of the now infamous Goldman Sachs. And it worked! I cannot find the exact amount of how much money he gave them, but it was enough for them to carry out the experiment. In contrast, when I wrote an email to David Solomon, the current CEO of Goldman Sachs, asking him for money to make this series of videos, he gave me a grand total of $0, which is equivalent to $0 in today's money. However, I now have something that Stern and Gerlach didn't have. Merch! That's right! Now you can buy this t-shirt with Emmy Noether, the one who discovered that the universe is made of symmetries. Or this one with Ralph Kronig discovering the electron. Or you can buy these images as stickers. You can buy them all in the link in the description, and they will be available for a month after this video comes out. Afterwards, we are gonna make all the orders and mail them, and if this goes well, I may continue doing it, but if it doesn't go well, this might be the only time I do this. So get them while you can. And of course, if you agree with Henry Goldman that science and science education are indeed valuable, you can just send me money directly, or you can join my Patreon. In exchange, I will bless your bloodline for 1,000 generations, and I will continue making these videos for all of you. Anyway, Otto and Walter did the experiment, and when they took the glass plate to see the results, they couldn't see anything. It was too difficult to distinguish the tiny silver deposits from other lights reflecting on the glass. But Otto was smoking, and the smoke contained sulfur, which reacted with the silver, creating silver sulfide, which is black. And this revealed two tiny black spots on the glass, with nothing in between them. This proved that quantization was real, and even more, it proved that, at least in some situations, you can measure the same thing and get different results. By trying to disprove quantization, Otto had accidentally created the strongest piece of evidence in its favor. And he did this because he was mistaken, not in spite of it. Like, think about it. Plenty of brilliant people were convinced that quantization was real, and yet none of them set out to do this experiment precisely because they were already convinced. Being wrong can be very, very valuable as long as you are willing to test your beliefs. And with this discovery, Otto had inaugurated the era of mistakes. Side note, while writing this, it came to me that this is similar to when Wu Chengxiong discovered parity breaking. Basically, what happened is that everyone, including her, assumed that the weak force had no preference for particles spinning to the left or to the right. But she and her friends decided to test it anyway, and it turned out that everyone was wrong. The weak force has a preference for particles spinning to the left. So remember to never believe in yourself. No, that's not right. Never trust anyone nor anything. No, that can be right either. Always have doubts? Is that right? I don't know. Let's move on. Otto Stern and Walter Gerlach published their results in 1922, and no one cared. Okay, that's an exaggeration. Exactly two people cared. Albert Einstein and Paul Ehrenfest. They got together and they tried to explain the results using everything they knew. But instead, they concluded that this was impossible using everything in known physics. Instead, they proposed new versions of this experiment using multiple sets of magnets. But this proposal was also ignored, or perhaps it was just too difficult with the current technology. And so, for the next 3 years, this experiment was nearly forgotten. I've read many papers from this time period, and very few of them mention it at all, and the ones that do are only citing it as evidence for quantization. They couldn't imagine that this experiment worked as a calcite crystal but for spin, as we explained in the previous episode. This gets even worse when you look at the papers from the geniuses, people like Heisenberg, Pauli, and Landé. I don't think they mentioned this experiment a single time during this time period, and I've read every paper they published between 1922 and 1927. So what were they doing instead? Well, Pauli was very interested in colloids, which is a kind of mixture in chemistry. I mean, look at this. Look at all of the papers he wrote about colloids. He worked so hard and got so far, but in the end, it didn't even matter. But I guess it's fine. I mean, we all go through our colloid period at some point, right? Meanwhile, Landé and Heisenberg were trying to explain the Zeeman effect using a new idea, quantum numbers. Part 2. The quantum number saga begins. Let me show you how I imagine that the quantization gang reacted to the Stern-Gerlach experiment.
Heisenberg Evil Incorporated.
What's this? You've proven that the orientation of electrons is quantized? This is much unexpected. And by unexpected, I mean completely expected. This has already been proven by the Zeeman effect. I mean, it's interesting you were able to prove it without using light. But it doesn't teach us anything new. However,
even if the Zeeman effect proved that the orientations were quantized, they still didn't know which other properties were also quantized in atoms. And knowing this was important for finding solutions to Ishihara's equation. But soon they realized that this was important by itself. Ishihara's equation could help you predict which transitions were more likely, and thus predict the intensity of the spectral lines. But it couldn't help you to predict the lines themselves. You were supposed to already know all the lines and use them to find the solutions. But think back to Rydberg's formula. This formula was able to predict all the spectral lines of hydrogen using the fact that the orbits are quantized. Well then, it should be possible to do the same with more complex elements. We would just need to use several quantized quantities instead of just one. In fact, this is precisely what Niels Bohr had been doing. A few months after Stern and Gerlach did their shitty experiment that no one cared about, he was giving a series of conferences in Bolskel where he explained the spectrums of nearly all the known elements using 3 quantum numbers, one for the orbit, another for the momentum, and the last one for the orientation. These conferences converted many skeptics to the gospel of quantum mechanics, but it also left them unsatisfied, because Bohr's theory predicted many spectral lines that were never observed experimentally, and Bohr admitted that this was a problem. It was clear that quantum numbers were a good idea, but it could also be improved. Maybe quantum numbers had some restrictions that Bohr didn't know about, and these restrictions made it so that some combinations of quantum numbers were impossible. Or maybe there were other quantum numbers different from what Bohr had imagined. This was the start of the quantum number saga. As scientists all over Europe would stare at tables of emission spectrums, trying to come up with better systems of quantized properties. These were called quantum number schemes, and they are an interesting chapter in the history of science because all of them were wrong. When I was in college, my teachers never told me about these alternative quantum number schemes. And why would they? They were paid to teach me things that were correct. But I think there's value in learning about how these people fucked up. For example, in 1923, Alfred Landé published this paper in which he proposed a new quantum number scheme. Here, J was the angular momentum, M was the orientation, K was the optically active electrons, and finally R was the angular momentum of the core. There's so much to unpack here. Okay, so for starters, notice how the orbit isn't a quantum number here. Alfred Landé apparently disagreed with Bohr that the orbit was a quantum number. There's also K, the optically active electrons, which refers to the electrons that are emitting light. And finally, we have the angular momentum of the core. What does that even mean? Now, compare that with this scheme that Heisenberg published in 1922. Here N is the orbit, K is the momentum, J tells you how much each line splits during the Zeeman effect, and finally M is the orientation. This scheme is clearly an improvement upon Bohr's work, and it is very different from the scheme Landé proposed, despite the fact that Heisenberg and Landé were friends who were very aware of each other's work. These were just 2 examples, but there were many more. Most of them were just variations upon Bohr's work, but others were completely different. And look, my autistic ass would love to go over every single quantum number scheme, but out of respect for my mental health, I won't. Instead, I will just point you to this paper by Edmund Stoner, real name, in which he compares many of the different quantum number schemes floating around at the time, by Bohr, Landé, Sommerfeld, de Broglie, Dauvilliers, Robinson. I gotta tell you, after reading all these papers proposing different schemes, it was very refreshing to see someone actually comparing them to each other. But looking at all of these different schemes, he made a crucial observation. In all of these systems, the number of electrons in each energy level seems to depend on the combination of quantum numbers. Like, some combinations of quantum numbers seem to allow for more electrons, while other combinations seem to allow for less electrons. Pauli found this observation so fascinating that it made him stop working on colloids for a change. He wanted to find the exact relationship between the number of electrons and the quantum numbers, and this is what he found. It seems that each electron in an atom has a unique combination of quantum numbers. Somehow they just never repeat. Today, this is known as the exclusion principle, although Pauli called it the housing policy. It makes me imagine the electrons as like little cartoon characters and each one has its own house. It's so cool. Of course, Pauli couldn't explain why this happened. He just proved that it happened. But still, this discovery completely changed the search for the true quantum number scheme, because now everyone had to take the exclusion principle into consideration. And then Pauli went back to researching colloids for no fucking reason! Okay, they were making all of these schemes and all of them were wrong, but little by little they were moving closer to the truth. And it was all thanks to the weird Zeeman effect. For the majority of elements, the Zeeman effect creates an odd number of lines, as if the line in the middle became many lines. And this was super easy to explain. It was literally the only quantum number everyone got right. For example, if you see 7 lines, that's because the maximum amount of angular momentum this orbit can have in the direction of the magnetic field is equal to 3 times Planck's constant. This is the dot product of the angular momentum of the orbit with the magnetic field. But remember that this is just the largest amount. The other allowed amounts are separated by 1 Planck constant. So for example, we can go to 2, to 1, to 0, and then to -1, -2, and -3. These 7 values give us the 7 lines we observe. At this point, they didn't know why this happened, but they could tell that it had to be related to some kind of symmetry in the shape of the orbit. But for some elements, mostly the alkaline metals, the line in the middle actually disappears, and so you get only an even number of lines, and no one knew why this happened, so this became known as the weird Zeeman effect. Well, okay, it was actually the anomalous Zeeman effect, but anomalous sounds like some kind of dinosaur. As you can imagine, there were many quantum number schemes trying to explain this, but most of them boil down to just ignore the zero and trying to give vague reasons for doing that. But then they had 2 ideas, a brilliant one and a shitty one, fractional quantum numbers and the atomic core. First, they looked at the separation between the lines in the weird Zeeman effect, and they found that the separation was always 1 Planck constant. And this was weird because if the line corresponding to the number 0 just became forbidden for some reason, then the separation between the lines to the sides should be 2 Planck constants, right? Not just 1. And they also found that there wasn't an extra orientation to one side or the other. No, they were symmetric, representing opposite orientations. How could both of these things be true at the same time? Can you help me? I'm trying to fit an even number of steps separated by a fixed distance in the number line, but I want to have the same amount of steps to both sides of the number 0. I want it to be symmetrical. Can you find a way to do it? No! No! Yes, correcto! Put them in the middle. Now all the values are fractions, but the distance between them is still 1 unit. When Niels Bohr initially proposed quantum mechanics, he had imagined that only a few fixed values were allowed. But this new idea flipped it around, suggesting that any value could be allowed, and what was actually restricted was the amount by which those values change. All of this is very nice in terms of mathematics, but now we go back to that question from before.
How can that be? Like physically, how can that be?
How can there be a fractional amount of angular momentum? I should clarify. Think how difficult it was to discover that the angular momentum was always an integer multiple of Planck's constant. And now that they finally proved it, it turns out that it's not always an integer. How can you explain this without contradicting everything you had already established? That was the problem. They didn't want to mess with the orientation. That worked really well for most elements, and it was probably correct. So they concluded that at least for some elements, there had to be some extra source of angular momentum. And that thing, whatever it was, could have a fractional amount of angular momentum. So far, so good. But here's where they fucked up. They didn't know what was the origin of this extra amount of angular momentum. And so, in 1922, Alfred Landé proposed that it came from the atomic core. And you might be wondering, what is the atomic core? And I was wondering the same thing. And apparently it's a term that is not used anymore to refer to like the cloud of electrons around the nucleus. But that didn't seem to make much sense. Like in the way these terms were used in the papers I was reading, it just didn't make any sense. And originally, a good chunk of this script this was spent describing the harrowing research journey I went into. But it wasn't very entertaining. So, okay, here's what happened. Eventually, I found a paper from 2002 in which a physicist called Andre Martin explained that at this point, there wasn't a clear definition of what the atomic core meant. For some people, it was just the nucleus. For other people, it was the electrons. For other people, it was all the electrons except the ones at the very top. So it seems that every person who used this word had a different definition in mind, and they just assumed that everyone else was using the same definition when in fact they weren't. And stupid as this may sound, I have come to the conclusion that, yeah, this is what happened. Humans are stupid sometimes, and this was the era of mistakes after all. Anyway, the problem now for the quantization gang was explaining why the core had a momentum of 0 for most elements and a fractional momentum for a few others. This was very difficult, and it got even more difficult once they discovered that if you ionized alkaline metals, their Zeeman effect went from weird to normal. But if you ionize alkaline earth metals, their Zeeman effect went from normal to weird. It was almost as if the addition or removal of one electron changed the momentum of the atoms by 1/2. Almost as if electrons had a momentum of 1/2. This seems so fucking obvious, and yet it must not be obvious because none of them noticed. Just imagine how many things people of the future will think are obvious, and yet we cannot see them. This is the context in which Ralph Kronig, Samuel Goodsmith, and George Uhlenbeck started learning quantum mechanics, and they would discover spin just a few months later. Part 3. The students come to the rescue. A long time ago, in a kingdom far, far away called Saxony, in the city of Dresden, a boy was born, and his name was Ralph Kronig. The Oracle, Wikipedia, says that both of his parents were German, but tomes of ancient lore says that at least one of them was from the United States. That would explain why they moved there when he was 14. He grew up there and then he went to university in New York, where he became an expert in the Zeeman effect. He wanted to do more research on this topic, but back then, if you wanted to do research, you had to go to the United Kingdom, Germany, or some other European nation. And so he took a trip to Europe in order to tour universities, meet people, and see what kind of opportunities could arise. This was the 20th century equivalent of sending a bunch of cold emails with your resume, except better because it's harder for them to ignore you. Anyway, Ralph arrived in Cambridge in 1924, where he met Paul Ehrenfest, one of the only two people who had shown interest in the weird Zeeman effect, remember? Paul Ehrenfest invited Ralph to spend a few months in Leiden University, in the Netherlands, and he liked to pair students together, so he paired Ralph with Samuel Goodsmith. Ralph and Samuel started doing some work on the weird Zeeman effect, and then Alfred Landé visited Leiden University, where he met Ralph, and then he told him that when his time was over in Leiden University, he should pay them a visit in Tübingen. A few months later, in December of 1924, Ralph went to Tübingen, where he and Ralph talked about the weird Zeeman effect, and then Alfred mentioned that one of his colleagues, Wolfgang Pauli, was working on a new quantum number scheme. Kronig read Pauli's draft, and he was rightly confused by the idea of the angular momentum of the core, probably because it made no sense. But then an idea just came to him, that if this was a momentum vector, and it didn't belong to the orbit, it could only belong to the electron itself. This was very similar to how planets spin around the sun, but also over their own axis. It was that simple. It was that simple! And it is such a logical idea that it is hard for us to understand why is it that no one else had thought about it before. After thinking about this for a long time, I've developed the hypothesis that the explanation is the mental framework people had at the time. And to explain what I mean, I have to start in a completely different place. Göbekli Tepe is one of the oldest archaeological sites in the world. It is even older than agriculture. Religion for Breakfast and Minuteman have very good videos about it. But what's interesting here is that the stones in this site are carved with images of animals. and they are all real animals. There isn't a single mythical animal carved in these stones. It seems that the idea of a mythical animal had not been invented yet. But eventually, every culture on Earth developed the idea of a mythical creature. And look at how they were described. Chinese dragons had the body of a serpent and the face of a horse. Assyrian Lamassu had the body of an ox, the head of a person, and the wings of a bird. This Minoan Griffith has the head of an eagle and the body of a lion. This Persian Simurgh has the face of a dog, the body of a peacock, and the legs of a lion. These creatures are fictional, but every part of them is real. It is as if real animals were like base vectors, but for thought. And these creatures were the result of humans learning to make linear combinations of these vectors. And for thousands of years, the vast majority of mythical creatures were like this, with very rare exceptions like the Hundun. I have no idea what's up with that one. But even when humans try to imagine aliens, they imagine them mostly like humans, like for example in True History by Lucian or in Micromegas by Voltaire. But then people started studying fossils, and Charles Darwin published The Origin of Species, and this added a new base vector for thought, the concept of evolution. And now people could use it to imagine truly alien aliens, like the Pearson Puppeteers by Larry Niven, or the Aliens from Expedition by Wayne Barlow. And who says we're done with this process? We can probably imagine even weirder shit, but we have no idea. Just like the people who made Göbekli Tepe had no idea what they were capable of. That was an example using mythical creatures, but I think this applies to everything. I think, my opinion, that we humans learn to think using frameworks. These are like vector spaces, but for ideas. And it takes a moment of genius to discover a new dimension of thought. But when that happens, that allows us to think new things and have new ideas. Think about this. People have known that emission spectrums were quantized for decades before Bohr came along. And they had even deduced some of the correct formulas by pure trial and error, like Rydberg's formula or Balmer's formula. And yet, they didn't realize that the orbits were quantized. And I think the reason for this is that they were taught to think about physics in a framework in which everything was continuous, because they went to university before Thomson discovered electrons or Einstein discovered photons. The genius of Bohr was using these new base vectors for thought, realizing that not only were the constituents of matter quantized, but also their speed and energy. This created a new framework to think about physics. They were able to imagine chimeras and sphinxes, but they still couldn't imagine aliens. They could imagine that particles could be in situations where their energy and momentum were quantized, but it depended on the situation. They still couldn't imagine that particles could have their own momentum, independent of anything else. This idea was the new base vector they had been looking for every time they created a new quantum number scheme, and they had gotten really close to it. When Ralph got this idea, he got really excited. He showed it to Landé and then to Pauli the next day, and as we all know, Pauli rejected the idea. And years later, German physics students actually made a small rhyme to mock Pauli for this. I imagine this is the kind of small but interesting historical detail that people come to my channel for. But now we can understand why Pauli acted this way. And in fairness, he wasn't the only one. After Tübingen, Ralph visited Copenhagen, where he met Niels Bohr and Werner Heisenberg. He presented his idea to them, but they also rejected it. After all, this was the era of mistakes. But what makes this especially frustrating is that Pauli understood he was looking for a new framework of thought. In his letters to Alfred Landé and Werner Heisenberg, he says that quantum mechanics would make sense once they invented the children's physics. Physics based on entirely new ideas created by young people. And he was right! He just never imagined these new ideas would come in the form of old concepts, like angular momentum or waves. Part 3.5. Funny anecdotes and matrix mechanics. And so everyone ignored Chronic. But at the same time, they all admired his intelligence. So much so that Heisenberg actually invited Chronic to work with him to develop a new mathematical model for the weird Zeeman effect that they could use with Ishiguara's equation. Sadly, this went nowhere, and Ralph decided to continue his journey through Europe. But before he left, he gave Heisenberg a piece of advice. Just work on something easier for a change. And so Chronic continued his journey through Europe, where he worked with many other scientists, until he settled in Delft University, in the Netherlands, where he would eventually become the dean. But what is even more interesting is that Pauli, Heisenberg, and Bohr would become really good friends with Chronic, and for the rest of their lives they would send letters to him every couple of weeks. And these letters are a treasure trove. For example, once Pauli told Chronic that he thought he could have been a great actor like Charles Chaplin, and that he regretted going into physics. That's real, that's something he actually said. But more often they would tell him about their work, and they would ask for his opinion on every tiny detail. So maybe Chronic should have some credit on everything these guys discovered after 1925. And what makes this even crazier is that even though Pauli and Heisenberg were both friends with Chronic, they weren't friends with each other. Don't get me wrong, they kept in touch because each recognized that the other was a genius, and they had a sort of professional respect for each other, but they didn't really get along. And in fact, once, Chronic made the mistake of telling Heisenberg what Pauli had said about him in another letter, and he freaking lost it, sending this letter to Pauli. Let me read you an excerpt from it. Okay, he said, "When you reproach us that we are such big donkeys that we have never produced anything new in physics, it might well be true. But then, you are also an equally big jackass because you have not accomplished it either. ... And then in parentheses, he also wrote this, the dots denote a course of about 2-minute duration. Close parentheses. Do not think badly of me, and many greetings." Like, I find very funny that he did not write the course words. Like, why not, Heisenberg? Were you afraid of monetization or what? Oh, and by the way, like, Pauli, Heisenberg, and Bohr weren't the only people sending letters to Chronic. Lots of other people were sending him letters. It seems that Chronic's greatest genius was in making friends. If only we could all be so lucky. But let's go back to Heisenberg. Chronic had told him to find an easier problem, and so he started thinking about Ishiguara's equation and how we had to write its solutions using Fourier series. And then he thought, let's say I have a Fourier series X that describes the position of an electron, and I have another Fourier series Y that describes the momentum of the electron. What would happen if I multiplied X times Y? He wanted to multiply position by momentum because the result is action. And if you want to understand why that is important, you should check out this video by PBS Spacetime, which I also wrote. Sorry. But you can think of it this way. We know how to multiply any two quantities in classical physics. It's super easy, they are just numbers. But if we want to multiply things in quantum mechanics, well, an infinite series by an infinite series is just infinitely many infinite series, and that's not really usable. So he just wanted to find a way to multiply things in quantum mechanics that made sense. Sadly, even this easy problem got so hard that Heisenberg decided to take a vacation, in which he continued working on the problem. This is the trip to the island of Heligoland that I mentioned in the previous video, and it concluded with Heisenberg discovering that x times y would be different from y times x. This made no sense with regular numbers, so Heisenberg discovered that he needed a new kind of mathematics, and this is why he thought he was the first person to use linear algebra, when in fact it had been discovered centuries before. It just had not been applied to this branch of physics. The whole logical and mathematical process that led him to this conclusion is extremely complex. And to be perfectly honest, I think that the way I described the role of linear algebra in quantum mechanics in the previous video was good enough. But if you want, you can read The Historical Development of Quantum Mechanics, Volume 2, Chapter 4, Sunrise in Heligoland to get all the juicy details. Heisenberg returned from his vacation, he published his findings, and everyone was amazed. It was clear that this was the beginning of a new era for quantum mechanics. But Heisenberg was understandably too exhausted to keep working on physics for a while, so instead his friends Max Born and Pascual Jordan set out to rebuild all of quantum mechanics using matrices, and they found something amazing. Previously, if you took an equation from classical physics, it wasn't valid in quantum mechanics. But now, if you replace the variables with matrices, it was indeed valid in quantum mechanics, which meant that they didn't need to depend on Ishiguara's equation anymore. For example, in classical physics, the total energy of a system is equal to its kinetic energy plus its potential energy. And in quantum mechanics, this is still true, except that you have to represent the momentum and the potential energy with matrices. Some of you may recognize this as almost Schrödinger's equation. And this is so frustrating, like when you want to scream at a character in a movie. Like, it's right there! You're so close! Don't let Schrödinger discover it, he's a rapist! But so it goes. What made this process difficult is that these matrices were always infinite. And since they are matrices, the order of multiplication matters. So you start getting weird things that wouldn't happen in classical physics. But all in all, it was still much easier than trying to tweak solutions to Ishiguara's equation. Part 4. The discovery of spin and the end of the quantum number saga. Meanwhile, back in the Netherlands, something interesting had been going on during all this time. Remember that Paul Ehrenfest liked to pair students so that they work together? Well, since Ralph Kronig had left, Samuel Goodsmith needed a new partner, and Ehrenfest decided to pair him with George Uhlenbeck sometime in early 1925. George was the less experienced of the two, and so Samuel started teaching him everything Ralph had taught him about the Zeeman effect and the quantum number schemes. It took them about a year, but while matrix mechanics was being developed, they continued learning about the different quantum number schemes and how they applied to the weird Zeeman effect. And at some point during this process, they came to the same realization Ralph Kronig had, that the angular momentum of the core made no sense, and that the fractional quantum number could only be describing the angular momentum of the electrons over their own axis. Like Ralph before them, they got really excited about this idea, and they showed it to their teacher, Paul Ehrenfest, who, unlike Pauli or Bohr or Heisenberg, was open-minded enough to recognize this was a valuable idea. And so he told them to make a formal report, and he would send it to be published in a magazine called Zeitschrift für Physik, which literally means physics magazine. And this was a huge deal. Like, everything important got published in the physics magazine. It was the physics magazine. They prepared the report, gave it to Ehrenfest, and then they showed it to another famous physicist, Heinrich Lorentz, who tore them a new one with criticism, pointing out that if electrons were spheres, they would have to be spinning faster than the speed of light for this theory to make sense. And so they literally started running, sprinting towards Ehrenfest's office, screaming at him not to send the report. But it was too late. He had already mailed it. Samuel and George were afraid of being ridiculed, but Ehrenfest told them not to worry. They were young and they could afford to make mistakes. But as we know today, they weren't ridiculed. I mean, sure, their ideas had a bunch of problems, but the scientists who read them quickly recognized its value because it allowed them to think in new ways. And so they began fixing some of the problems, like proposing that particles were point-like and not tiny spheres, as so many people had assumed. With the discovery of spin, the saga of the quantum number schemes had finally ended, because scientists realized that they could explain all the spectral lines in the weird Zeeman effect using only 4 quantum numbers: the spin, the orientation, the momentum, and the orbit. This was basically the same scheme Bohr had proposed half a decade ago, with the addition of spin and the exclusion principle. Although, funnily enough, people had already been using the letter S to refer to the angular momentum of the core, so it is a complete coincidence that it matches with the name of spin. Part 4. Finding the math of spin. But the era of mistakes was not over yet. There were two new discoveries at the same time, matrix mechanics and spin, and everyone wanted them to kiss. They all wanted to represent spin using matrix mechanics, and a few more mistakes would be made in the process. First, Team 7 was skeptical about spin, and they had no intentions to investigate it. But then, Bohr was invited to a party that Lawrence was organizing for the 50th anniversary of his PhD. That's right, he was throwing a birthday for his degree. Anyway, the point is that Bohr went to this party, he started discussing spin with another guest, and by the end of the conversation, he was a convert. Can you guess who convinced him that spin was a good idea? That's right! It was Albert fucking Einstein! We can't escape him! He's the Forrest Gump of physics! Then Bohr convinced Heisenberg to look into spin, and Heisenberg tried to use his new matrix mechanics, but he couldn't figure it out, so he resorted to using Ishikawa's equation and Fourier series. Oops, that wasn't quite right, sorry. It is true that Heisenberg couldn't describe spin as a matrix, but instead of using Ishikawa's equation, he decided to represent the magnetic field of the hydrogen atom as a matrix, and this included the effects of spin. What I say next is about this approach. And his results were correct! Well, kinda. His results were twice as big as they should have been. The energy, the momentum, everything was twice as big. If his results were larger or smaller by random amounts, he could have admitted he was wrong. But the fact that they were twice as big every time meant that he was very close to the right answer, so he must have been doing something right. And yet, it was not the right answer. So it was evidence he was doing something wrong, but he couldn't figure out what it was, and neither could anyone else. Heisenberg sent letters to a ton of people asking for help, but none of them could find any mistake in his calculations, and so he decided to call on the smartest man on Europe to help him, Wolfgang Pauli. Except that Pauli wasn't feeling like it. Pauli's reply basically amounted to, "I told you spin made no sense, dummy. No wonder your calculations are wrong." This started a period of time that I'm calling Pauli's diva era, because everyone could feel that they were on the edge of something great, but they could also sense that the next few discoveries were gonna be very challenging, and so they all wanted Pauli to get on the game. A bunch of scientists got together to try to convince him. Bohr, Sommerfeld, Einstein, Born, Ehrenfest, they all sent him letters begging him to stop working on colloids and work on spin instead, but it didn't work. Heisenberg and Kronig were debating him constantly about why spin actually made sense, and yet he still refused to work on it. But if the geniuses won't do their goddamn work, the students will come to save them. This is how we meet the first member of Team 10. Enter Llewellyn Thomas. And if you are Welsh, please tell me if I got it right, I practice a lot, but for the rest of the video I'm just gonna call him Llewellyn. Okay, so Llewellyn had just started his master's degree, and he decided that while Pauli was making them work for it, he was actually gonna work on it, and to everyone's surprise, he actually fixed Heisenberg's mistake. The key was relativity. Everyone had underestimated the relativistic effects, but Llewellyn didn't. And when he did his own calculations, he found that the only difference with Heisenberg's result was a factor of 1/2 multiplying everything. This cancelled the factor of 2 that no one had been able to fix. At this point, Bohr sent a letter to Pauli, informing him of this new discovery, and he said, "Now, however, comes the surprise for the learned relativity theoretician and the scientist laden with responsibility." Let me translate what I think Bohr meant to say in modern English. Surprise, motherfucker! A student just solved the problem that you refused to work on, and the answer was relativity, the thing that made you famous in the first place. When are you gonna understand that your genius gives you the responsibility to use it? With great power comes great responsibility. Also, we're gonna publish his result on Nature. How's that? At this point, Polly had to admit that he was wrong and... No. Polly said to board that Llewellyn was wrong and that they shouldn't publish his mistake in Nature because it would be humiliating. Fucking asshole. And don't worry, they of course didn't listen to him. At this point, someone actually convinced Samuel Goodsmith to travel to Hamburg and preach to Polly in person that Llewellyn was right, and yet Polly still refused to accept it. However, a few weeks later, something amazing happened. Polly's heart grew 3 sizes, and he finally admitted that spin existed and Llewellyn was right. And as penitence, he wrote letters to all of these people admitting that he had been wrong all along. And you know what? Respect. Admitting you were wrong is difficult for a normal person. For Polly, it must have been fucking agony. But he still did it. Another big problem was the idea of zero spin. Electrons had only been observed to have a spin of 1/2 or -1/2 Planck constants, but they suspected that maybe electrons could have a spin of 0. That was until Lucy Menzig, the second member of Team 10, broke into the scene, proved that a spin of 0 was impossible, and then fucked off, never to be seen again. This is infuriating for me, because I would love to talk about more women in these videos, but shortly after making this discovery, she quit physics to become a homemaker. And you know what? I just hope that this was her choice and that it made her happy. Then, Polly finally started working on spin, trying to use it to make more precise calculations of the energy levels of hydrogen. Just to find that a student had published those exact same results just a few weeks earlier. His name was Paul Dirac, and we will hear a lot more about him in future episodes. And this actually hurt Polly. In his letters to his friends, he mentions how guilty he felt about wasting so much time. And he was right. This new branch of physics was running out of discoveries, and fast. But there was still one important discovery left. The first one, the one that Heisenberg couldn't do. How to represent spin using matrix mechanics. Polly decided to focus on this problem, and he succeeded, finding the Polly matrices. Wait, no, this makes no sense. This is Polly's most famous paper. Here he proved how to represent spin using matrices. This is the beginning of quantum field theory, of humans understanding that nature is made of symmetries. And yet, while reading it, I couldn't shake the feeling that something was wrong. I can't explain why, but the reasoning Polly presents in this paper makes no sense to me. Or well, of course it makes mathematical and logical sense, but it made no sense that anyone would reason this way, not even a genius. And it just felt as if a piece was missing. He never mentions the Stenger-Lach experiment, and he mentions the Zeeman effect exactly twice. That's very suspicious. Eventually, I contacted some of the best science writers in the world, like David Griffiths, to see if they could answer some of my questions about Polly's reasoning, but they couldn't help me. I was in the hole, there were no more clues. Had Polly really deduced his matrices just like that? I mean, if anyone could do it, it was Polly, but then what was I gonna say in the video? I wanted to give people a logical progression everyone could follow, but it seemed I would have to give up on that. I decided to read Polly's paper one last time to see if I could get an insight into his genius, when I noticed something. At this point, Polly had finally given up and accepted that spin existed. but he was still bitching about something called double-valued functions and how they were superior to the idea of some other chump, a fella named Darwin. I had read that line dozens of times by this point, but I had never bothered to see what was this idea Polly was dissing so much. Until now. I looked up this Darwin fella and what do you know? It blew the case wide open. Finding Darwin's papers was like a revelation. This was the missing piece I had been looking for. Suddenly, everything made sense. Darwin was aware that people were now using matrices and vectors in quantum mechanics. But these were abstract vectors without any clear connection to the physical world. They were just a useful mathematical tool. But then there was the problem of spin. And he realized that the spin vector was being changed in a similar way as the polarization vector of light when it passes through a calcite crystal. The polarization of a wave could be represented as a vector. Matrices multiply vectors. Matrix mechanics was the new way to do quantum mechanics. And then there was this French guy called Louis de Broglie who said that maybe all particles were also waves. All of these ideas combined in Darwin's mind like vectors, guiding him to an unexplored region of idea space. Maybe the polarization of matter waves was the spin. But even this was a mistake too. The polarization of matter waves is the probability of having a certain spin. But still, this was close enough to the truth for Darwin to feel its importance. He developed the idea as much as he could, he published his results, and Pauly read them just in time. Pauly did not like this idea of waves and polarization for the same reason he didn't like the idea of spin. It was too normal, and so he decided to tackle the problem of spin once and for all using new and different ideas, but they were just Darwin's ideas in disguise. He literally says, I'm not gonna use waves, I'm gonna use eigenfunctions. But to anyone who learned quantum mechanics after 1930, these are synonymous. They are literally the same thing. Even if he didn't like Darwin's ideas, he couldn't unlearn them. This was a new base vector in his mind, and he couldn't help but use it. And this is how the era of mistakes finally ended, with Pauly insisting a theory was wrong at the same time as he was using it. Even when he was right, he found a way to still be wrong. Classic Pauly. But of course, soon enough, everyone realized that Darwin was right. The correct way to think about particles was not using double-valued functions, but instead by using probability waves represented by vectors. This was the era of mistakes. And I wanted to tell you about it because in life we will be wrong most of the time. But if you have the right attitude, that can be very useful and very valuable. You can be like Otto Stern or Chen Wu, putting your beliefs to the test. You can be like Heisenberg, tirelessly searching for the truth. You can be like Bohr or Sommerfeld, accepting new evidence and new ideas. Hopefully you can be like the students, tackling difficult problems with a fresh mind and finding new ideas. And finally, you can be like Pauly, accepting when you were wrong and taking new ideas to their final conclusions. But there is one thing I know that wasn't a mistake, and that's you making it to the end of the video. Thank you so much for watching, and thanks to everyone who supports me with donations or in other ways. And especially I want to thank a few people. First of all, Ivo Danihelka. You've helped me only once, but you helped me so much. I will be grateful to you for the rest of my life. Carlo Fazioli, you've helped me to change my life for the better. I can never repay you. Manuel Marquez, you motivate me to make these videos and do them better and better. You have no idea. Lana Montegazza, without you, the quality of my videos would be far lower. OtiumOtiosum, you were the first person to donate me money in Patreon ever, and you've been with me since the beginning. Thank you so much. And finally, I want to thank my other patrons who also have helped me immensely. Valerie Hyde, T. Highfill, Alec Luhman, Daniel H. McGillivray, Robert Bigman, Richard Allen Park, Metarus 208, Ryan Roberts, Jadon Hansel, Azure Azalia, Edward Hoff, Matthias Zerdin, Cookies of Tea, Sinos Fantu, Marlo Brown, EDS2, Matix Vai, Edie Kosek, Martumate, Dan Babich, Pedro Almeida, and Josh Stein. All of you, thanks 1,000 times, thanks 1,000,000 times.